Good afternoon, everyone. My name is Adrian Garcia, and let me say I'm delighted to be here today to talk about the role of plant simulation in the era of smart factories. Today we'll see what smart factories are, which technologies drive them, and what is the role of the digital twin in all of it. But first, let me quickly introduce myself. I'm a senior virtual factory consultant with 10 years of experience in discrete event simulation, mainly working with plant simulation. I leave you here my contact information in case anyone wants to reach out to me later. During all these years, I've had the opportunity to work in several industrial sectors. However, most of my career has been for the automotive industry, first working for SIEMENS and later for Gestamp, which is one of the largest automotive tier 1 suppliers worldwide. Due to the great technological knowledge and innovations accrued by Gestamp during all these years, many companies have requested our consultancy services, and to be able to provide such a service, Alona, the company I work for now, was born a year ago, and since then we've been growing strongly and incorporating top profiles from other industries to provide our clients with the best solution to their challenges. Alona specializes in several digitalization technologies, such as IoT or data science, allowing us to create a digital ecosystem for our clients. In my case, I am responsible for the virtual factory department, where we apply simulation tools, such as plant simulation, to a wide variety of scenarios, from simple capacity analysis to more complex projects, such as developing commercial libraries or heuristic optimizations. And it's precisely this digital ecosystem, all under the Industry 4.0 paradigm, that boosts our factories to the next level. And here I'd like to stop for a moment to see the differences between a digital factory and a smart factory. Most of the industry has reached the F1, an automated and robotized factory with a variety of digital tools implemented that generates loads of information and data that is widely available across the company, and it's crucial for decision taking. In this scenario, for instance, logistics and production simulation, like plant simulation, plays an important role. But smart factories represent a real breakthrough in the industry. We are not only talking about having automated processes or taking informed decisions, which is important, but to make the software take the decisions for us. In other words, smart factory is able to manage itself and adapt all its assets to any change in the production conditions. And here we need more sophisticated tools, so we are no longer talking about simulation, but about digital twins. But what exactly is a digital twin? Because right now it's become such a mainstream concept that I'm sure that if I ask this question to 10 people, I probably get 12 different definitions. Well, talking with other colleagues in different congresses, I heard things like a digital twin is a 3D representation of a product, or a digital twin is a real-time representation of the status of a facility. But for us in Alona, those definitions don't bring anything new to the table. A digital twin is a digital model of a real-life product process or system, and it must have the logic that represents this process behavior. So if we have the same inputs in both the physical and the digital twin, we should get the same exact results, so we can use it to make predictions. So far, I could be still talking about a really detailed simulation model, but there's one main difference here, that the digital twin must be constantly updated with information and data from the real system. And here is where the digital ecosystem that I referred before plays an important role. Thanks to tools like IoT or data science, we can have that constant flow of information to input in our models. So let's see how all these technologies have a real impact in the industry with an example. As I mentioned, I worked for Gestamp before Alona was created, and there I had the opportunity to participate in a revolutionary project called Factory 21, which solved one of the key problems in the automotive industry using a smart factory. So here we have a typical automotive welding line. All the assets here are dedicated to produce a few different references for a specific car model. And this line will be in use for as long as that car model exists, which normally lasts from 3 to 5 years. And after that, all this line will be dismantled. So one of the main problems here is how do we size the line's capacity? Well, normally car manufacturers work with an estimation of how many cars they expect to sell, which looks something like this. Here we have the total number of cars versus the timeline that, as I said before, is from 3 to 5 years. And since this line is dedicated for a specific car model, Gestam as a supplier must design the line's capacity to reach the highest ratio of production that is expected. But what usually happens is that the real volumes that the car manufacturer sells never reach the expectations. So we end up with all this overcapacity here that obviously has a huge impact in our product's price. Well, to solve this problem, Gestam developed the Factory 21, a smart factory with a modular design that is able to produce any given reference in any of those individual production cells that you see here in the picture. And not only that, but also the total number of production cells can be increased and reduced easily. So now the installed capacity looks something like this. But now we need the factory to manage by itself thousands of references and decide not only when to produce a reference, but also where to produce it. So how do we do it? Well, we started by designing this digital architecture for the automatic planning and sequencing of the facility. We defined a deterministic algorithm that controls the general management of the facility, coordinates all these assets, and is able to implement any given planning. This plan manager is constantly checking for any deviation in the current planning, and if it detects that something happens, may it be demand change or production line failure or a quality loss, to name some, when anything happens, it executes the digital twin, which, as I mentioned before, is constantly being updated with the information from the facility. And then the digital twin calculates which is the optimal way to optimize the resources and meet the new demand. But now we face another problem here, that is, how does a digital twin know which combination of thousands of references and tens of production lines is the optimal? Well, we solve it using generic algorithms, which mimics Charles Darwin's evolution theory. Picture this: we have the first generation of any given species. I use here turtles, but it works with any other species. And that first generation must survive in their environment. So those individuals who possess specific characteristics that make them more fitted for that environment will statistically live longer, so will also statistically reproduce more and pass those characteristics to the next generation. And in this reproduction process, some mutations may occur that create new characteristics that are not inherited from the predecessor. So always, statistically speaking, the second generation will always be more adapted to that environment than the previous one. And if we repeat this process over and over, with each generation, we will have better adapted individuals. So basically what we have here is a natural and automatic process that optimizes the problem, which in this case here is the survival of the species. But we can apply the same logic to our planning and sequencing problem. We start by creating a random set of initial plannings, a first generation of initial plannings, which are here represented with strings of binary data. And we are going to evaluate how adapted they are to the environment, which in our case means how good they are in optimizing our production. And here is where the digital twin plays the key role, because what we're going to do is run simulations with each of those individuals and give them a score depending on how good they were in optimizing the production. Once we've got this, we select the best ones, combine them, apply some mutations, and get a new generation. And if we repeat this process enough times, we will reach a point in which there is no significant difference between one generation and the next one. And at this point, we can stop the algorithm and take the best individual from the last generation as our result, which in our smart factory context means that then this result, this planning, is returned to the general plan manager so it can be automatically implemented in the factory. So, after all we've seen, these are the main messages I wanted to share with you today. Industry is evolving towards a smart factory as they further optimizes productivity and efficiency. The digital twin and plant simulation play an active and important role in making this possible. And by combining all these technologies with genetic algorithms, we can unlock operational excellence. Thank you.
Thank you, Mr. Garcia. Questions to the smartness of factories?
Yes.
Would you just explain the outcome that comes out of this digital twin and tells us how to operate the smart factory?
Mm-hmm.
Is it like a heuristic that's used for
Yes.
multiple things, multiple products, or is it made for each product?
No, it calculates the whole factory at once.
Okay, so in what time frames are we speaking? How
So-
often is this updated?
Every time there is a change in the production conditions that triggers the plant manager.
And what would constitute a change in production conditions?
Well, I've given a few examples. For instance, a failure in a production line that is not calculated before, is not a preventive maintenance, or a change in the demand in the short term that affects the current planning. Things like that may have an impact in the production.
Okay, so it could be multiple times a day, it could also be just once in every 2 weeks or so.
The key things here is that the smart factory is able to adapt constantly to any change.
Okay.
So the software is the one that takes the decisions, not us.
Alright, thank you.
Yes.
About optimization components and the genetic approach that you mentioned, what was your objective function? That it tries to minimize or maximize something?
Yes.
That make this system and then go for the next one, for the next loop.
We took into account different KPIs, but as I said before, I no longer work for Gestamp, so I cannot really share more information that I did. But yes, it's a combination of different KPIs that has a good estimation of how good it was, the production. Yes.
I have a question concerning the simulation optimization approach. Did you use the library inside plant simulation for the GA wizard, or did you implement the genetic algorithm outside?
No, the embedded library for genetic algorithms works pretty well, and it has all the work done for the automatic execution of the runs and etc. So yes, you can. We did it with that, and I think it's the best option. Yes.
Has the Factory 21 project that has been initiated by Gestamp been done together with an OEM or with
No.
any other partners or
No. No. Only
separately only Gestamp?
yes. More questions? Okay.
Okay, thank you.